Hello everyone, welcome to Advanced Structural Testing course. My name is Yuguang Fu. I'm a postdoc at Purdue University. Today we will study experimental modal analysis. This is the outline of today's lecture. We will firstly introduce the background of the modal analysis and then quickly go through the basic knowledge about modal testing in the lab. After that, we will study how to apply different methods using measurement data to obtain the modal properties, including frequency domain methods and time domain methods. And all of these methods that we discussed in the lecture will be evaluated in the benchmark problem for structural health monitoring and dam detection, and then compare their performance. I will also describe the demo that I will show in tomorrow's lecture in MATLAB. And finally, I will give some summary and conclusions. All right, so let's start with the background. Modal analysis is the process to obtain modal properties, such as natural frequency, damping ratio, and mode shapes. It has been widely used in many areas, such as structural engineering, electrical engineering, and aerospace engineering as well. So why the modal analysis is very important to all of us? Well, it's actually play a key role in especially the design of and simulation of dynamic systems. One of the studies is the structural dynamic modification. So how it works? So usually we will have finite modeling, and we will also have the modal testing from the lab. And then once the model has been validated and verified, then we can use that model to simulate and to evaluate any change that we made to the design, right? And without building a physical system with this change again. So in that case, it can help us to identify the weakness of some specific locations of the dynamic system, and then propose and evaluate the change of the improvement. We can also use that modal analysis result to do dam detection, right? For example, impedance-based dam detection is based on the peak value shifting, which is resonant value, resonant frequency here, to use as indicator to infer the dam location. We can also use the modal analysis result to mitigate the mechanical system vibration, right? It can help us to design the vibration absorber or base isolation such that the system, the excitation frequency is away from the resonant frequency of the dynamic system. All right, so now let's quickly go through some basic knowledges that about modal testing in the lab. I believe all of you already studied about that in the previous lectures, so let's just quickly go through that. Okay, imagine we have 3-story building model. For sure, to obtain the dynamic response, we need sensors. Okay, and one of the most widely used sensor, most common sensors, is accelerometers. We can put accelerometers on each floor to measure the acceleration response, right? Also, we need devices to provide excitations. Typical excitation device could be hammer to provide impact testing. We can hit in each floor, right? And we can also use the shaker. Similarly, we can attach the shaker to the different floor of the structure using the stinger here. And the other device is the shaking table. So, but shaking table is usually put in the bottom, the base of the structure to provide ground motion. Okay, and the figure on the right shows the typical structural response in subject to the impact given by hammer, and the shaker test, and also the shaking table test. So once we have the measurement from both the output and the force, then we can obtain the frequency response function. That is actually one of the fundamental equations or information that we will process in modal analysis. Okay. So the figure shown in the right-hand side is the matrix of the FRF plots. Okay. And the number of columns shows the number of sensors. Okay. And number of the rows represents the number of the impact location. Okay. So for example, the top left figure shows that if we hit the hammer, if we use the hammer to hit the structure on the first floor, then if we directly use the first floor acceleration response measurement, we can obtain this FRF plot here. And this is exactly what we discussed before, is the driving point. So the driving point is the location where the force, the excitation, and the measurements are in the same location. Okay. And for that corresponding FRF, we will have the peaks representing the resonant frequency. We also have zeros representing the anti-frequency between each poles here. Okay. And so the off diagonal shows the FRF where the impact location and measurement location are not in the same place. Okay. So one thing you can notice that you can observe that it is the matrix actually is symmetric, meaning that you can obtain the same FRF if you hit the structure, for example, in the third floor, and then use the second floor measurement, or you hit the structure in the second floor, and you use the third floor measurement. You can exactly obtain the same FRF. This actually represents to the figure here in the second row, and the figure here in the third row. Okay, they are actually identical. So this is what we call reciprocity features for the FRF modal testing in the lab. Okay. All right. So now let's talk about the strategies or methods we are using to extract the modal properties using the measurement data. So again, following the FRF plots that we discussed before, we can extract the modal properties using peak-peak methods. This is one of the fundamental basic strategies that we will use in the lab. So it based assumption that the FRF at certain resonant frequency is dominated by only that vibration mode, right? And in that case, the FRF plot can be separated into different. The FRF plot of the multi-degree freedom system can be decomposed into several single degree freedom FRF plots. So this is exactly showing how we decompose that and obtain the 3 single degree freedom FRF plots. Okay, omega 1, omega 2, and omega 3, which exactly represents the first, second, and third natural frequency. And also we can use we can use half power methods to extract the damping ratio here. Okay. Regarding mode shape, how do we do that? How do we obtain that? Well, we need to first plot the imaginary of part of the FRF plot. So again, we obtain the matrix of the plot here, and then to obtain the first, second, and third modes, which easily just obtain that by connecting the the first peaks in the different figures in the first row of the FRF plot. Okay, so this is actually the first mode. You can also obtain that in the second row, the third row as well. Okay, for the first mode. The second mode, you can first find the second peak, second resonant frequency actually, and then for example, and then connect the peak value in the first row figures. Okay, and then you can obtain the second mode. You can also obtain the second mode in the second row figures and third row figures as well. Similarly, you can obtain the third mode here. Okay, so this is what we obtain the modal properties using peak-picking methods. It actually easy to visualize, but actually not quite accurate because it mainly depending on the peak values without utilizing other information in the other frequency domain signals. Okay, and in most cases, it may not easy to identify the natural frequency because of the frequency resolution. Okay, so one extension about peak picking method is that if the force measurement is not available or inaccurate, instead of using the FRF plot, we can also utilize power spectral density to extract the natural frequency and mode shape. So by checking the auto power spectral density, we can obtain the natural frequency, which is exactly the resonance frequency here, omega 1, omega 2, and omega 3. And we can also use cross power spectral density to approximately extract the mode shape, right? But in that case, we need to select one measurement as a reference. Okay. So here, for example, we can use the third floor measurement as a reference, and then obtain the mode shape as the ratio of the cross spectral density with respect to third floor divided by the auto power spectral density of the third floor measurement. Okay. So here we can obtain the phi 1, phi 2, and phi 3 corresponding to the mode shape. So the second method about frequency domain mode analysis is the frequency domain decomposition. It is an extension of peak picking method and proposed by Brinker in 2001. First of all, I think everyone understand that the relationship between the input and output can be described as y of omega is equal to the FRF function h omega times x omega. Okay, and assuming that the entire process is stationary, we can obtain the power spectral density of the output measurement is actually equal to the h star of omega, which is actually corresponding to complex conjugate of the h function, okay, times the power spectral density of the inputs and times the h transpose of omega. H is the FRA function, is with the size of m times r, which it can also be expressed in the partial fraction form here. Okay. Then, assuming that input is white noise, we can simplify the power spectral density of the input to be a constant, and then we can substitute it into the expression of the output power spectral density, and also we can substitute the FRF expression in this formula as well. Okay. Assume that the damping is light, and then the residual which corresponding to the denominator in these items, they become proportional to the mode shape, and also we can claim that in a certain frequency, only a limited number of the modes contribute to those the magnitude of the power spectral density of the measurement. Okay, so we can further simplify the expression of the output power spectral density as it is. Okay, and sub omega represents the list of the limited vibration modes that contribute to the power spectral density magnitude or other information surrounding that omega frequency. Okay. All right. So this is the theoretic background of the frequency domain decomposition. The next question is, how do we implement that? Okay. Well, the first step is to compute the power spectral density of the output matrix. Okay. So Y matrix consists of the each item from Y1 until Ym, and it has the dimension of M times R. M is the number of measurements, and R is the number of samples. Okay, and then we can obtain the matrix of the output power spectral density as it is. Okay. The next step is to compute the singular value decomposition of output power spectral density. Is actually equal to U sigma, U lambda, and V transpose. Okay, and U, which is the left eigenvector, can help us to obtain the mode shape based on assumption that at each peak value the corresponding mode is dominated. Therefore, UI1 can be used as the approximation of the mode shape. Okay. The next step is to compute the natural frequency and damping ratio. For each peak, for example here, this is the singular value, the first singular value plot against the frequency. Okay, and for each peak, we can first isolate that peak and transform back to the time domain. Here, we can equivalently obtain the free vibration of the single degree freedom system. Okay, and by using logarithmic decrement method, we can obtain either both the natural frequency, which is equal to the inverse of the TD here, and also the damping ratio. Okay. Now let's talk about time domain methods. The first time domain method is the Abraham time domain. ITD is proposed by Abraham in 1973 to deal with the free vibration response data. It based assumption that any free vibration response can be expressed as the combination of a linear combination of the certain modes. Okay, and phi 1 is phi I, phi 2, phi n is the mode shape, and also the second item here, e to the lambda 1 t lambda 2 t, is actually corresponding to the eigenvalues in S domain. Okay, and then we can build the Y matrix that consists of the n samples. Okay, and it can be decomposed into two parts: the mode shape and the eigenvalue in Z domain. Okay, matrix and mode shape matrix and eigenvalue in matrix in Z domain. Okay, and then next step is to shift one dt, and then we can build a one Y hat, which exactly has the same dimension of the Y matrix, but it actually include additional item in the decomposition into decomposition formula here. Okay, and we can utilize that to define a system matrix A, which has the dimension of n times n. Describe the relationship between the Y and Y hat. Okay. After substituting Y hat of Y into the equation above here, and we can simplify the equation this expression of A and further obtain this formula, which is exactly the eigenvalue decomposition if a formula of the A matrix. Okay, and phi here is the mode shape, and lambda here is the eigenvalues in the Z domain. To obtain the model properties, we can do eigen decomposition of the system matrix obtain the mode shape, as I mentioned before. And also we can transform from Z domain to S domain and further to continuous system to obtain the natural frequency omega k and the damping ratio zeta k here. Okay. The second time domain methods is called stochastic subspace identification methods. SSI is widely used over 2 decades for system identification. It's based on the stochastic state space model. The unique part is that instead of having UK as the input, it utilizes WK and VK to represent process noise and output noise. They are both considered as the white noise process. Okay. Assuming the stationary process with the zero mean, we can obtain these results corresponding to the expectation of the state vector with respect to n times the WK and VK here. Okay. And then we can define the output correlation matrix lambda I, and this lambda I is equal to expectation of YK plus I times YK transpose. And then the other matrix is G matrix, which is next state output matrix, is actually equal to expectation of XK plus 1 times YK transpose. By substituting all of these above equations into the, this equation into the expression of the output correlation, we can obtain that lambda I is actually equal to C times A to the K minus 1 times G. Okay. We can further utilize that to construct Hankel matrix and Toeplitz matrix. First, let's build a Hankel matrix using the output measurement. So the Hankel matrix has the feature that the anti-diagonal terms are the same. Okay, and the special operation of the Hankel matrix establishing in SSI is that we need to divide this Hankel matrix into 2 parts. The hot part corresponding to past measurements. The first part corresponding to past measurement, the second part corresponding to future measurements. And that we use YP and YF to represent them. Okay, and then we can compute Toeplitz matrix TI slash I is equal to YF times YP transpose. And we can build this block Toeplitz matrix. The Toeplitz matrix has a feature that the diagonal items are the same. Okay, and each item in this Toeplitz matrix is lambda I, is actually the output correlation matrix. Next step is to factorization of the Toeplitz matrix. It can be decomposed into 2 parts. The first one is the observability matrix, and the second part is the stochastic controllability matrix. We use V and W to represent them. By taking singular value decomposition, T actually can be equal to PDQ transpose. Okay, and we can further do truncation of the singular values by examining the magnitude of the singular value here. Each actually, by excluding 0 singular values, it can be simplified as Pn, Dn, and Qn transpose. Okay, and then we can obtain the realization of the observability matrix and the stochastic controllability matrix. Vi is equal to Pn times Dn to the 1/2, and Wi is equal to Dn to the 1/2 times Qn transpose. Okay. The next question is, how do we obtain the system matrix from the Toeplitz matrix? Well, we need to first shift 1 dt for the Toeplitz matrix. As we shown before, so Ti here is only Ti slash I, T1 slash I is actually equal to the Vi times Wi. Okay, if we shift 1 dt, we can have the external item here, which is A matrix in between V and W. Okay, and then we can obtain A matrix by inverse by multiplying the T2/I+1 times the inverse of the V and omega. Okay, and by substituting the observability matrix and controllability matrix into this formula, we can further obtain the detailed expression of the A matrix. Okay, and how about the C matrix? C is actually the first item of the observability matrix, so we can directly obtain that by selecting first row of the VI. L is the number of outputs. To further obtain the model properties, we need to do the eigendecomposition of the A matrix, and the mode shape is equal to C times psi, and the natural frequency and damping ratio is exactly the same as we discussed before for the Abraham time domain methods. Okay. There are two variations of the SSI. One is SSI BR, represent I think it's the basic realization, and the second is CVA, represents kinetical variate analysis. So the difference is that they use different weighting matrix. SSI BR using their identity as the weighting matrix, but CVA use the kinetical variant analysis to maximize the correlation of the measurement at different locations. Okay. The third time domain method we are going to study is the eigensystem realization algorithm, which we also call ERA in short. It is developed by Joan and Papart in 1984 for model parameter identification and model reduction from test data. It has more accurate results, and also widely used in different areas. Okay, it's based on the deterministic state space model. Okay, the objective is to obtain the triplets of the ABC as the system realization for state equations to satisfy the given input and output. Okay, so first we can obtain the solution of the discrete state space equation. YK is actually equal to C times SK is equal to C times two items here. Okay, and first item corresponding to the solution subject to initial conditions x0, and a second term corresponding to the response subject to the external input. Okay, and based on that, we can obtain the two unique items. The first one is the free vibration. YK is equal to C times A to the K times x0, which is corresponding to the first item here. Okay, and the second is the impulse response, which is YK is equal to C times A to the K minus 1 times B, is corresponding to the second term here, assuming that the input is the impulse. Okay, and Y is the matrix with the size of P times M. P is the number of measurements, and M is the number of the inputs. Next step, let's form a Hankel matrix with the size of R times S block using impulse response. Okay, and we can decompose into three parts. The first item is the observability matrix, and second item is the system matrix, and third item is the controllability matrix. Therefore, HK minus 1 is equal to VR times A to the K minus 1 times WS. Okay. Similarly, Similar to SSI strategy, we can do single value decomposition of the Hankel matrix. But here, we only deal with H0, meaning that K is equal to 1. Therefore, we will not have system matrix in the middle between V and W. Okay, and H0 is equal to PDQ transpose. And similarly, we can do a truncation of the single value by checking the magnitude of the single value in this D matrix. Okay, ideally D0 is or equal to 0, so we can easily identify the number or the rank of the Hankel matrix. So eventually we can obtain that H0 is approximately equal to Pn times Dn times Qn transpose. But in practice, D0 are not always 0. Okay, so we need to define the threshold to differentiate Dn and D0 for us to do the truncation of the singular value. Okay. All right, so next step is to obtain the system realization, which is to obtain the ABC matrix utilizing the Hankel matrix. So first of all, based on H0, we can obtain the observability matrix and controllability matrix. They are actually equal to Pn times Dn to the 1/2, which is corresponding to VR, which is observability matrix. And the other term is the Dn to the 1/2 times Qn transpose, which is corresponding to Ws. It is controllability matrix. By shifting 1 dt, we can, by shifting k from k to 1 to k to 2, we can obtain k1 here, which we can obtain h1 here. As I shown here, if k is equal to 2, we will have a system matrix in between the observability matrix and controllability matrix. Okay, so therefore we can obtain the A matrix. It is actually equal to the V inverse times H1 times Ws inverse. Okay. We can also obtain the B matrix and C matrix. B matrix is actually the first item of the controllability matrix here. So we can just select the first block in this matrix. And C matrix is the first item in the observability matrix. So we can similarly obtain the C matrix by select the first block here. So eventually we obtain the ABC matrix expression using the P, D, Q, and E here. The next step is to obtain the modal properties by eigenvalue decomposition of the system matrix A. Okay. Similar to SSI, we can obtain first lambda matrix, which is diagonal matrix of the mu1, mu2, and to mu_n. They are actually in the Z domain. Okay, and then we can transform back to the S domain, obtain lambda k, and further by comparing real part and imaginary part, we can obtain natural frequency and damping ratio. And regarding mode shape, is actually equal to C times psi, and is equal to EP transpose times Pn times Dn to the 1/2 times psi. The other important item is called initial model amplitudes is equal to psi inverse times B is actually equal to psi minus psi inverse times Dn to the 1/2 times Qn transpose times En. Okay. All right. So now we already go through the other theoretical background of the ERA strategy. So let's discuss some questions for the implementation. The first one is, how do we determine the size of Hankel matrix? Especially, how do we determine R and S? Okay, as I mentioned before, Hankel matrix consists of each output measurement block here, y is actually has a size of p times m. P is the number of the measurement, m is the number of the input. And therefore, Hankel matrix is actually has a size of PR times ms. Okay. Many researchers have tried out different strategies, and they come up with the rule of thumb here. So they claim that we need at least 2 columns for each mode, and eventually the number of columns is actually equal to 5 times 2 times expected modes. For example, if we want to have if we want to identify 3 modes, then we need at least 30 columns. Okay, and for the number of rows, it can be computed as 2 or 3 times of the column number, right? So if we want to identify the first 3 modes, then we need around 60 to 90 row numbers. Okay, and usually we will try 90 numbers in the row here. And next question is, how do we determine the number of singular values? Well, we can plot them, right? In the ideal case, it can easily differentiate the singular value corresponding to genuine modes and a singular value corresponding to the noise mode. Okay, so this is the plot in the ideal case, right? So the red curve shows the signal, and corresponding to genuine modes, and the blue curve shows the noise modes. Okay, we can choose the right value by comparing this significant value of the singular value plot. Excuse me. But in practice, it's quite challenging. Look at the figure on the top right figure. We can see that we have densely plot of the singular values, and it's very difficult to differentiate the singular value corresponding to genuine mode or the singular value corresponding to the noise mode. Okay, therefore we need to use stabilization diagram to address that. Okay, the basic idea is that if the mode is genuine, it can always be identified for any size of the singular value, any number of singular value, right? As long as we have sufficient singular value to process that mode. So here's how to plot, how to look like. So the stabilization diagram, first of all, have their average power spectral density to provide the reference for us to visualize the potential modes. So each peak represents 1 potential mode. Okay, and in the left-hand side, we also have the singular value retained starting from 0 to 120 in this example. Okay, so for example, if we select 60 singular values, then we can obtain several modes, right? Each marker here represents the modes that it identified. Okay, so for example, it first identified the first peak and also the third peak here for the corresponding to 60 singular values. Okay, similarly, we can repeat that and then obtain all the identified modes are marked in this plot for a different number of the singular values. Okay, and if in this plot some modes have many numbers of marks representing that it's very stable for different number of singular values, then we can claim that those modes are the modes that we are expecting to identify. So that actually corresponding to, that's why we have this red circle plot here to identify those stable modes. Excuse me. All right, so the next question is, how do we determine the qualified modes using accuracy indicators? Right? Even though we already obtained the potential genuine modes from the stabilization diagram, we still need an indicator to quantitatively measure how much that we can trust this mode to be a genuine mode. The first indicator that a researcher has proposed is modal amplitude coherence, which is also called MAC. It basically compares the modal amplitude time history reconstructed from the initial conditions with identified eigenvalues against the one that we directly extracted from the measurement data. So MAC compare the vector of Q bar and Q hat. Especially it estimates the angle between these two vectors. The cosine value of the angle between these two vectors. So if it is 0, meaning that these two vectors are perpendicular. So these two modes are not the same. Okay, totally different. But if it is 1, meaning that the mode shape, meaning that the vector Q bar and Q hat, they are identical. Okay. So Q hat is actually the modal amplitude time history from measurement data. It's actually equal to psi inverse times dn to the 1/2 times qn transpose. And Q bar is actually modal amplitude time history extrapolated from initial conditions and identified eigenvalues. Okay, so the initial conditions is Bi is actually equal to psi inverse times dn to the 1/2 times qn transpose times en. Okay, and then we can obtain this we can extract the modal amplitude time history in a specific time sample in specific time by multiplying the initial conditions and the eigenvalue. Okay, in the z domain. So this is one of the fundamental noise accuracy indicator to quantitatively measure if the modes that we obtained is genuine or no. Okay, but it's not actually very powerful. It's not very accurate. Therefore, researchers extend that EMAC to be extended modal amplitude coherence. So basic idea is that we need to first extend the Hankel matrix by adding one additional row and one additional column in the end. So this is the last block column. By default, it shifts by 10th sample. It is actually corresponding to T is equal to Ti, T input. Okay, and the last block row is also shifted by 10 samples. Is corresponding to T is equal to T output. Okay. Let's first obtain the accuracy indicator based on the output, which is corresponding to mode shape components. Okay. First of all, let's obtain the initial time history, initial mode shape response. Okay, and this actually corresponding to the first block row here. So phi ij0 is actually equal to C0 times psi, okay, which is actually equivalent to extract the first block row of the mode shape components, mode shape block. Actually, that actually equal to a Pn times Dn to the 1/2 times psi, okay. And we can also predict the mode shape components at the time T is equal to TO, and it's actually equal to phi ij0 times e to the lambda I times TO here. The next step is to extract the mode shape components corresponding to the last block row here, okay, and the result is that phi ijTO is equal to CTO times psi, okay, which is actually equal to the process that to extract the last block row of the P and DN to the 1/2 psi matrix. Okay, and then we can compare the measurements, the mold shape component extracted from the measurements from the last plot row, and the mold shape component extracted from, predicted from the initial conditions and the eigenvalues. Okay, so we should compare the phi ij and phi ij tilde. And well, for comparison, because they are complex numbers, we first compare their magnitude, obtain the ratio of their magnitude. Second, we also compare their phase difference. Okay, this is the formula to quantify the phase difference here. And eventually we can obtain the output EMAC is actually equal to Rij times Wij, which combine the magnitude comparison and phase comparison. Similarly, we can do the same analysis, the process of the modal participation factors which corresponding to the inputs. We can obtain the gamma ij0 corresponding to the first block column, which is equal to psi inverse times b, and then we can predict the gamma ij at t is equal to ti by multiply the gamma ij0 times e to the lambda I ti. Okay. We can also extract the modal participation factors from the last block column. Okay, and then we obtain the gamma ij ti here, and eventually we can compare gamma ij tilde and gamma ij at t is equal to ti. Similarly, we can obtain the input EMAC, which is the multiplication of Rij times Wij. Rij corresponding to the magnitude comparison, magnitude ratio, and Wij is corresponding to the I think this is the phase difference. Okay. And for the specific mode I, we can obtain the EMAC corresponding to the jth inputs and kth outputs. Right? We can just multiply them, the input and output EMAC together. And eventually, we need to condense all the EMAC results from the matrix to a single value. Okay. All right, so the next question is, I think it's the last question about the implementation is how do we determine the inputs for ERA to build a Hankel matrix? As we discussed before, we can use free vibration, YK, to build a Hankel matrix or impulse response function, right? And if it is force vibration, as long as we have force measurements, we can first build the transfer function and then obtain the impulse response by doing inverse Fourier transform. But what if we don't know the inputs, especially in the ambient vibration, right? Where it is very difficult to measure the ambient vibration for the inputs, right? How do we do that? Well, we will study two popular strategies to address that. The first one is the natural excitation technique, which is also called NEXT. So NEXT is to calculate the correlation of the ambient vibration proposed by James in 1993. Let's look at the equation motion here. Here, x of t and f of t are both stochastic random displacement and force vectors. Okay. Based on that equation motion, we multiply each item of that motion equation with a reference measurement signal, xref. And then we can obtain the expectation, obtain this equation here. And each item here, expectation, for example, expectation of xt double dots times xref x is actually corresponding to cross correlation of the output measurements with respect to the reference measurement. Okay. So here we can further simplify it as approximate equation motion that corresponding to the cross correlation. Okay. And consider the ft, which is the force vector, is white noise, and also the reference signal is uncorrelated with the input. Therefore, we can cancel out the right-hand side as 0. And also, the derivative of the correlation holds that the correlation of A and B, if A is the derivative of time, then we can move the derivative to the correlation, right? So eventually we can say that we can obtain this equation of motion here, and the derivative is actually corresponding to the correlation of the measurement, of the displaced measurement. And tau is actually equal to T minus S, okay? By taking the fourth derivative of this equation, we can further obtain this the second equation here, that's telling us the correlation of the acceleration can also be used, and can also be used here and satisfy this equation. And eventually, we can claim that we can treat this correlation function as a free vibration, right? And it can be used as input for the ERA. All right, so this is the next strategy. That it deals with the free vibration data, it deals with the ambient vibration data, and eventually we can obtain the cross correlation of the measurement data corresponding to a reference measurement data, such that we can use that as the input for the ERA. The second strategy that has been widely used is the random decrement technique, which is also called RDT. It's proposed by Cole, which assumes that dynamic response of the structure under ambient excitation is organic. Let's look at the signal here. By defining so this signal is selected as a reference signal, and then we define a triggering condition such that every time when the signal satisfy the triggering condition, we will start to collect the data until it fill out the buffer. For example, here we collect half-second data as long as the vibration exceed or is corresponding to 0.5 here. And then we average all of these blocks that we obtain, right? For example, 1, 2, 3, 4, 5, 6, until 13, 14, etc. All of these half-second blocks, we average them together, and eventually we can obtain approximately free vibration response. Okay, so this is the formula here describes the structural response due to both initial conditions and the random load. Okay, and by averaging a large number of time segments of the same initial conditions, the response due to the random loads will disappear, right? Because they are random loads. Okay, and therefore we can treat the random decrement function, which is corresponding to the first item here, can be considered as the free vibration response. So to utilize the RDT strategy, we need to define auto random decrement function and cross random decrement function. So auto random decrement function dxx tau is actually equal to the summation, the average of the summation of the measurement data corresponding to the triggering conditions. Okay, and the cross RD function. So auto RD function is the it actually it actually refer to the measurement data and the reference data. They are the same. Okay, and the cross RD function is a similar formula, but the measurement data is not the same as the reference measurement data. Okay, so for the mathematical proof, excuse me. For the mathematical proof, we can expand the RD method as the expectation, and eventually we can find that it is actually a function of the cross correlation and auto correlation of the measurements. Right? If we consider positive points as trigger condition and further simplify the formula, they are actually dx's and dxy actually is a function of rx's and rxy. And record that in the next strategy, we can use cross correlation as approximate free vibration data, right? And eventually, equivalently, we can also use random decrement function to satisfy this homogeneous equation, differential equation, to resolve and use RD function as the free vibration data. So in the end, we can also use RD function results as the input to ERA or SSI or other strategies to do model analysis. So next section, I would like to describe about the application that we found in the paper written by Yi and Yun in 2004. They use AAC benchmark problem to evaluate the performance between different model analysis strategies. Before talking about detail about their strategy accuracy, let's first describe some background of the AAC benchmark problem. So it is actually a frame structure, and the physical structure is sitting in the University of British Columbia, and correspondingly, it has the numerical model to represent that. Okay, and the neural model actually has a total number of 16 measurement data. On each floor, it actually has 4 floors here. On each floor, we have 2 sensors for X direction and 2 sensors on Y direction. Okay, so eventually we have 16 measurement data. And in the analysis, the authors use random roof excitation, and then to obtain the vibration from the 16 sensors. The vibration has 40 measurement duration. Okay. So let's first look at the result from the frequency domain methods. The left figure shows the result from peak picking methods, and right figure shows the frequency domain decomposition results. Okay. And in the left-hand side, we can see that for the power spatial density function, we cannot for some power spatial density function, it will miss some peaks. Right, for example, for Y15 corresponding to the 5th sensor in top floor, it actually cannot identify the second peak here, which corresponded to 11 Hertz. Similar for X, for the 16th measurement data, it cannot identify the first peak. So it has some missing peaks here. But eventually, if we combine all of the auto PSD function together, we can obtain this. We can identify all the modes here. Okay, and for frequency domain decomposition, we are interested in the first singular value of the power spatial density, and we can see that it successfully identified all the modes that we are interested in. Actually, it has 8 modes here. All right. So for time domain methods, let's first look at the stabilization diagram, because Abraham time domain method doesn't have that stabilization diagram. So here in the paper, we only have the stabilization diagram for ERA, SSI, BR, and SSI CBA. Okay. As you can see here, they actually did a very good job in terms of to identify the 8 modes, all of the 8 modes. Okay. First, second, third, fourth, fifth, sixth, seventh, and 8. Okay, and by looking at this diagram, we can conclude that SSI/CBA did the best job, right, to identify the modes. Given there's, I think there's 20% or 10% measurement noise. Now let's quantitatively look at the frequency, the natural frequency identification. Okay, so the table here shows the natural frequency of the 8 modes. So we have BY1 represent the first mode in Y direction, BXY represent the first mode in x direction, and similar for by2, bx2, and eventually by3 and by4 and bx4. Okay, and the mode shape here showing the first four modes in x direction, and equivalently we will also have the first four modes in y direction. Okay, and we have the exact value ground truth from the model. And let's first look at the frequency domain results. We can see that peak picking actually doesn't do a very good job in terms of the accuracy. So the average error is about 0.14%, and FDD did a much better job than peak picking. For time domain methods, Abraham time domain is not quite accurate compared to the rest of time domain methods, and ERA and SSI CVA, they both did the best job in terms of the accuracy of the natural frequency. Okay. Secondly, the figure here shows the comparison of the natural frequency error with respect to the noise level. So circle means there's no noise, and triangle means there's 20% noise, and the cross means there's 60% noise. So and the figure here shows the x-axis shows the mode number, okay, and the y-axis shows the accuracy, the error, okay. So as you can see here, both frequency domain methods they do not did a good job in terms of the accuracy for the first three modes, okay, and also for ITD as well. And for ERA and SSI, they did quite a good job in terms of that. Secondly, let's look at the effect of noise level on the accuracy of natural frequency identification. You can see that, again, ITD is not quite good when the noise level is high, but ERA and SSI, they did quite a good job in terms of the, they are quite robust to the noise level. The second comparison that is showing here is the mode shape comparison with the noise. So again, we have the frequency domain methods and the time domain methods in the bottom four figures here. So one thing we need to pay attention to is this number 6 and number 7 modes. You can see that almost all of these figures has a relatively lower MAC value to which meaning that the mode shape accuracy is quite low. Okay, so this is because number 6 and number 7 modes, they are closely spaced to each other. So if we look at the natural frequency in their number 6 and 7 modes, they are actually very close, right? One is and they are all around 14 hertz. Okay, therefore it is challenging to successfully accurately identify the mode shape. So that challenge actually is not handled well for peak picking and FDD and ITD methods, but the ERA and SSI, they did quite a good job to address the challenge and eventually obtain the relatively accurate mode shape. All right, so that's the comparison between different mode analysis applied on the benchmark problem. Later on in tomorrow's class, I will show the demo in the MATLAB. I will first use the lab test from 6-degree freedom model, which is sitting in the ISO lab at the University of Illinois at Urbana-Champaign. We have 6 sensors, and each of them is deployed on each floor. And the sampling frequency 128 Hz, and we have a total number of half minutes measurement data. And the measurement data will have 2 excitation inputs. One is hammer testing. The hammer hit different locations of the floor, and also we have the shaking table to emulate the ground motion and random excitation. Okay. The second demo I will show is to apply the mode analysis to the field test data from Guangzhou New TV Tower. So this is Guangzhou New TV Tower is located in China, and it has sensors deployed in different height of the tower. So here we use 20 accelerometers deployed on 8 levels to do model analysis. So we have 10 sensors in strong axis and 10 sensors in weak axis. So this is strong axis, this is weak axis, okay? And the sampling rate is 50 Hertz, and we have 24-hour measurement data to process that, okay? So in this field test, we don't have any input measurement. So we will use output only model analysis strategy to identify that, the model properties, okay? All right, so now let's talk about this. Now let's summarize what we learned in today's lecture. First of all, we have elaborate the background and importance of the model analysis, and also we quickly go through the basic knowledge of the model testing in the lab. After that, we study about frequent domain methods and time domain methods, and eventually we apply that to we examine their accuracy and compare them by checking their result in the benchmark problem. And tomorrow we will show the demo in the MATLAB. Sounds great. So that's it for today's lecture. Thanks for your listening, and thanks for your attention.